Yeah, hi. Thank you, Anderson. I couldn't unmute myself, but now, yeah, thank you. Okay, so let's start with today's lecture, and feel free to ask questions in the chat or raise your hand if you have questions. And yeah, I'm happy to be interrupted. Okay, let me share my screen. Okay. Okay, so today's lecture is about data structures. So we'll first talk about kinds, which is something that some of you have already asked about before. So a kind is basically the type of a type. Then we talk about persistent data structures and explain why it's not horrible for performance to do what Haskell does, that all our default data structures like lists, for example, are persistent. So we never update anything in place. Instead, we always, if we want to change something, we actually don't change it. We basically create a new thing. And that sounds as if it would be highly inefficient, but actually it's not. So we'll look at that. And then we'll look at two useful practical data structures that are not in the base libraries, but in a very commonly used package called containers. I actually already used that briefly, I think, or at least mentioned it. And finally, we'll talk about nested data types, which is more like an XCOS. Okay, so let's start with kinds, sorry. And for that, let me switch to GHCI. And if I ask for the type of undefined, I mean, we have seen that before. If you ignore this constraint here, that's a relatively new addition. It's just to get like call stacks and error messages. Basically, undefined is of any type A. So, I mean, we can, for example, we can specialize it. So we can say undefined int, and that's of type int. But what happens if I do undefined maybe? Then I get an error. And so the question is why? I mean, somehow we think undefined can be of anything, can be any type. So why can't I put maybe there? And I mean, one thing you might think is maybe always needs something. I mean, if I say maybe, for example, bool, then it works again. So maybe one like hypothesis would be that it's never allowed to use maybe on its own. It always needs a type parameter or some concrete type applied to it. And there's let's see what it's called in the slides. Wrapped int. So data wrapped int. Just check. Okay, and if we have that, which is unusual, then we can do something like example 1, which is of type wrapped int maybe. And x1 is wrap, for example, just 42. And that compiles perfectly fine. So there we do have a naked maybe. And we can do it with other types, for example, example 2, wrapped int list. Example 2 is wrap 1 to 5. Or we can do example 3, wrapped int IO, and say wrap readline. And all these examples compile. And it's quite unusual because it's not often that you see something like maybe or list or IO naked like this without being applied to a type. But as you can see, this is definitely possible in Haskell, which brings us to kinds. So we did see an example where maybe can appear without a type parameter. And if in this example I do wrap just 3, as I did in example 1, and if I now here instead of maybe say maybe int, which might seem reasonable, then I get an error, and it's a so-called kind error. Expected kind star to star, but maybe int has kind star. So that's this one. And I mean, we have talked, I mean, in Haskell, types are very important. And we have seen a lot of types since this course started. And type classifies Haskell expressions. And I mean, mostly expressions, but one could also say patterns or declarations. And only well-typed expressions are admissible. So for example, something like 3 plus a, I mean, an int plus and then a character would not be well typed, and the compiler would reject it. So types are a way to basically tell us whether an expression is well formed or not. And if it is, then an expression has a type. And kinds that we haven't mentioned before do basically what types do for values or expressions, kinds do for types. So type is a kind is like the type of a type. So where values, expressions have types, types have kinds. And only same as for expressions that you can write something that the compiler rejects, like 3 plus the character a. You can also have types that the compiler will reject because it's not well kinded. And the kind system in Haskell, at least if you don't activate all sorts of extensions, is much simpler than the type system. So the most important kind in Haskell is called star. And in more modern versions of GHC, you can also call that type. I mean, instead of star. So star and type is the same. But here in the class, or in this course, we mostly stick to star. And basically all expressions in Haskell have a type that has kind star. So if you define an unparameterized data type using data, that type that you define will have kind star. So you can think of kind star as the kind of potentially inhabited types, or as the kind of fully applied types. So whenever you can write down a value, something, I mean, a concrete value of something that has a type, and then that type of that value will have kind star. So int will have kind star, a list of ints will have kind star, maybe bool will have kind star, everything where you can write down a value, the type of that will be of kind star. These are simple examples. So int, character, bool has kind star. Maybe int functions from int to int, lists of characters. Tuples consisting of a boolean and a function from character to lists of functions from ordering to IO actions. Wrapped int maybe. And also, I mean, type variables are also allowed. So A to B to A. All of these things here on this slide have kind star. And if you now look at something like maybe, then you can see maybe as a function on the type level. So you give it an argument, which must be a type, and it returns a new type. And question is, what are we allowed to apply to maybe? So for example, can we do maybe IO? And actually we cannot. And what we can only apply something to maybe that is potentially inhabited, so that has kind star. And therefore, maybe gives us an example for different kind. I mean, until now we have only seen things of kind star, but maybe actually has kind star to star, where this function arrow is the same. I mean, it's also functions, but now not for values, but for types. So this says maybe has kind star to star, which means if you apply maybe to something of kind star, like int or character or functions from ordering to IO action or whatever, then you get something else from kind star. So again, something that's inhabited and that has values. And as for types, we mentioned that in principle, for GHG, at least if you don't activate all sorts of extensions, you never need type annotations. It's just good practice to annotate at least top level declarations in Haskell with the type signature. And that Haskell in principle can infer all the types. And in the same way, Haskell can also infer kinds, same way as it can infer types. But you can ask GHCI for the inferred kind of a type. And we have often, when we played with GHCI, used this :T to ask for the type of something. And there's also :K, which is an abbreviation for :kind, to ask for the kind of something. So we can demonstrate that. So let's start with, for example, int. And it tells us int is of kind star. I can ask kind bool. That will also be of kind star, or whatever, functions from bool to list of int will be of kind star. But if we ask it for the kind of maybe, it's star to star. So maybe is something that takes a type of kind star and gives you another type of kind star. So for example, the kind of int we saw is star, and the kind of maybe int is also star. Maybe applied to int, something of kind star gives us something else of kind star. And I said everything of kind star, that's types where you can potentially write a value of that type, which we can. I mean, we can write, for example, 3 of type int, and we can do something like just 5 type maybe int. But we can't write down a value of type maybe. We can write down one of maybe int or maybe bool, but not of maybe itself, because maybe does not have kind star. Right, and we have seen several examples, so maybe it's not the only one. For example, monad like IO is also kind star to star. For example, put getLine is type IO string. So IO is also something that takes something of kind star and gives us something of kind star. Same with lists, list of int, list of bool, list of characters, list of functions from int to int, and so on. Then pair is actually of kind star to star to star. So in order to get something of kind star, we need to supply 2 arguments of kind star. Zum Beispiel pair of int, bool, or pair of list of strings, IO actions, something like that. Then triples accordingly is of kind star to star to star to star. So we need to fill in 3 holes of kind star to get something of kind star. And again, of course, that we can check all of this in GHGI. So kind whatever int bool list of maybe character. Sorry. Would then be of kind star. The function arrow. So we have like the type of peer images and the type of images. Both need to be of kind star. And that gives us a new type of kind star. Or the state monad. It takes also 2 arguments, the type of state and the result type, and gives us something of kind star. So we have seen all these examples already. And actually, until now, when we use the function arrow or pairs or lists, we always use the special syntax that Haskell provides for that. But actually Haskell also allows you to use prefix notation for that. So this here, arrow int list bool is the same. I mean, I can ask for that. So I mean that accepts, Haskell accepts this. And it's of kind star. That's the same as what we would normally write into list of bool. So Haskell also allows to write these types, function and list in prefix notation like this. Also pair. I could also say pair of, for example, character and Boolean. That's the same as what we normally write, character or bool. Okay. And now we can say why undefined maybe didn't work. Because undefined is a term. So whatever its type is, must be of kind star. But maybe is not of kind star. As we just saw, maybe is of kind star to star. Therefore, this doesn't work. And this doesn't work because maybe is of kind star to star, but IO is of kind star to star, not of kind star. So we can't apply IO to maybe. So there's also a kind error. And now what's the kind of wrapped int? So wrapped int takes this f, and here we see that f is obviously something of kind star to star. So wrapped int is of kind star to star to star, which is like a quite unusual kind. I mean, we haven't seen that before. And the parentheses here are important. I mean, something like pair was star to star to star, but there the parentheses would be on the right-hand side. So this is different here. And therefore, wrapped int maybe is correct because wrapped int expects something of kind star to star as its argument. But something like this would not be correct because maybe int is kind star and not star to star. And this kind system, that's basically built into Haskell, but normally you never have to explicitly mention it. I mean, you can ask GHCI, as we just saw, with :k or :kind for the kind of something, but you never have to mention it in your code anywhere. But you can if you want, and you add explicit extensions. So for example, this wrapped int, I could annotate this. So I could say, explicitly say that f here is of kind star to star, and that this f int then, sorry, and star. Okay, fine. Now I get illegal kind signature, but I can enable this kind signatures. And now that should compile again. Okay, and there's even another extension that you can give, like you can give type signatures to functions, for example, or to top level values. You can also give kind signatures to types, and then it's starts with the keyword type. So I could say wrapped int is of kind star to star to star. And that will also complain because for that I need yet another extension, and that's called standalone kind signatures. Sorry. I hope that works. Yeah. Okay, so they say that these days instead of star one should write kind type, which I'm mentioned earlier that you can, instead of the star, you can also write type, but then you need to import data.kind. So if we wanted to be more modern, we could say data.kind star, sorry, type. And then everywhere where I wrote star before, I can now write type. And then this warning would get away. I can remove this actually. And I think then I don't need this anymore. And this is just complaining because it says it should be a new type instead of data. So if I want all warnings, okay, fine. I want to get that give. Okay, I don't want any warnings. Do it like this. Right, so type and star is the same thing, but type is in this module here, data.kind. So if you want to use type instead of star, you have to import this. And I mean, star is a bit strange because it's the parser for Haskell code needs some special treatment for the star. And it seems they want to deprecate that in one of the future versions of GHC, so that you always have to say type. But as I said, this is never, I mean, if you don't do like very advanced Haskell with lots of extensions enabled, you never need these type signature, these kind signatures. But sometimes they can be helpful, especially with an unusual kind like this. So that this star to star is quite unusual. So this wrapped int is a weird type that you won't see often in actual Haskell code. Okay, mentioned this. So, are there any questions at this point? Okay, if not, then there's one. So until now, basically all the kinds we have seen are of very simple structure. I mean, either it's star or it's some kind, arrow, some other kind. So basically, there are just stars and arrows so far. The picture gets a bit more complicated when we also look at type classes. So something like class eq or functor that we have seen. So I mean, here, for example, the A has to be of kind star, but what is the kind of this eq or of functor? So we could say that, for example, here the A needs to be of type of kind star and the F needs to be of kind star to star. And actually, one needs another extension to talk explicitly about the kind of constraints. So that's constraint kinds. So if I activate that and ask for the kind of eq, for example, then it tells me it's of kind star to constraint. So I need something of kind star, for example, int, and then I get something of kind constraint. So eq int is a constraint. Eq maybe would not be well kinded. So constraint is the stuff you are allowed to write in parentheses before function signature, for example. Function can have the constraint that you need eq a or something like that. So constraint, that's like another primitive kind. So we had star for the stuff, I mean, star as the kind of types that are inhabited or potentially inhabited, where you have values of that kind. And now we have kind constraint as the kind of things that are constraints. So for example, the kind of functor, it takes something of kind star to star, something like maybe or list, and gives me a constraint. So here are some examples. So eq and show both have star to constraint. So we have something like eq int or show string. Functor takes something of kind star to star. So we have functor maybe, functor list, functor IO. Applicative and monad have the same kind as functor. So we have instance monad IO or applicative list. And okay, so that's that. So we have star, constraint, and this arrow, the arrow on the type level to build our kinds. So nevertheless, the kind language is much simpler than the type language. I mean, we have seen dozens of types already, or maybe even more. And the kind language is still very simple. I mean, it's just the star, the constraint, and the arrow symbol, and then like using those to build more complicated kinds. And same as functions are typically curried in Haskell, types are too. And often we also only partially parameterize them. So for example, we could write an instance, I mean, that's already defined for us somewhere in the base libraries, instance monad either E. So remember, either is takes two, we can check it out. I mean, either is of kind star to star to star. So we have something like either bool int or either string, whatever, list of characters. So the kind of, if I only apply one, it's same as with current functions. If I give one argument, then either int is of kind star to star. And kind star to star is exactly what, for example, monad expects. Monad expects something of kind star to star. So it's well kinded to write monad either int, for example. So that's exactly the same as it also works for functions, normal functions. So here again, so either is kind star to star to star. So if I apply an E, if I apply this, then what I'm left with is kind star to star. And that is exactly what I can apply monad to. So monad either E makes sense. Monad either wouldn't make sense because monad expects something of kind star to star, but either has star to star to star. Okay. Or a similar example would be functor, comma, t. So explicitly, so that's this here is the type of pairs where the first component is a t and the second one is open. So it's still then, I mean, pair is same as either, goes from star to star to star, takes two parameters, one for the first type of the first component, one for the type of the second component. So here we fix the first component to t and the second one is still open. So what is left after applying this t is of kind star to star, and functor takes something of kind star to star. And if we specialize fmap to this type, then we get fmap from A to B, functor applied to A to functor applied to B. And this is just, I mean, prefix notation for this here. So that this is a functor boils down to writing fmap of this type. So given a function from A to B, can I write a function from pairs of T's and A's to pairs of T's and B's? And of course I can. If I have such a pair, then I just keep the first component as it is and apply the given function to the second component. So that's why this is indeed a functor.
Lars, we have a question. So
okay.
Can the kind concept be equated to generics in Java or C++?
I think that's two different things. I mean, polymorphism is what can be equated to generics in Java or C++. So the fact that we can use type variables, but that's different to what we're doing here. I mean, here basically.
Right. So the generics are on the same level as types. I mean, there are types, more general types, but kinds are in a different level, are on top of types.
Yes. I mean, generics is, I mean, whatever. I mean, we had this example, let's say swap in bool or whatever. Maybe not a good example, but I mean, I can have a function like this. And then I can realize that it doesn't matter that it's int and bools. It would work for arbitrary types. So I can generalize that. I mean, I can, and the name is not appropriate anymore. I can just generalize this to arbitrary types, but this a comma b here, so this would be generics in Java, that I have a function that, or also a type like whatever, data, for example, my weird pair. Something like this. This would be generics in Java, or I mean that I have data types and functions where I can still fill in the concrete types. So this would work for int and bool, but it would also work for character and string or whatever. That's generics. And or this type, I mean, like lists, for example. I can have list of ints, but also list of bools, and I don't have to need one version per concrete list type, but I can basically have this generic list type, this polymorphic list type. But the kind of, I mean, the kind of int comma bool is star, but the kind of, okay, that doesn't work. But the kind of something like this would also be star. I mean, it doesn't work in GHCI because then it complains it doesn't know what A is. But so generics is a different concept to kinds. I mean, this here also, both sides have kind star. That has nothing to do with the fact that it's polymorphic in A and B. It's nevertheless kind star because I can write values down of this type. So kind is really a level higher. Same as you can, I mean, certain terms are not allowed because they are not well typed. Certain types are not allowed because they are not well kinded. I mean, same as I said before, you can't say something like 3 plus A, that gives a type error. I mean, it's maybe a bad example. What's a better example? Whatever, you can't do to upper true. If I had to upper in scope, I mean, that gives a type error because to upper, the type of to upper is character to character, and the type of true is bool. So I can't apply to upper, which expects a character, to something of type bool. And exactly the same happens on the kind level. If I do, for example, maybe list, it gives me a kind error because the kind of maybe is star to star, and the kind of list is also star to star. So I can't apply this kind, I mean, something of this kind to something of that kind. That's exactly the same as I can't apply true to upper. I can't apply list to maybe. Here it's on the type or on the value level. So the types don't match. And here it's on the kind level. The kinds don't match. So yeah, it's a level above types. And I think, no, it has nothing to do with generics. It's like orthogonal to that. Are there other questions?
Not for now.
Okay. Right, so we looked at currying. This is the instance I mentioned before, so it's easy to write that. So given a function and a pair, then you just keep the first component of the pair constant and apply the function to the second component. Right, and then of course one might ask, what about this function? I mean, we have this fmap for this functor instance of pairs. Which applies the given function to the second component. And of course, it would be perfectly valuable to write this function. So I mean, we can try this out if you want. So fmap I don't know, show, for example, fmap show applied to the pair true and x, would leave the first component alone and apply the given function show to the second component. And of course, I could also define a function which looks very similar, but which leaves the second component alone. The definition is almost exactly the same. So I just apply the function to the first component. Now I could do fmap whatever to upper c comma false, fmap prime, sorry, which works just fine. But the point is the functor instance only works like on the second component, and we can't somehow make this an fmap on the first component. So it really matters in which order the type parameters are applied. So in the case of pairs, I mean, it's the first argument of this functor, or this this type constructor is the first component, and the second is the second component. And because of this currying, in order to make it of the right kind, namely star to star, I must apply one argument. So I must fix the first component, and then I can have a functor instance on the second component. I can't easily get one, or not at all actually, on the first component. So there is no way to basically partially apply types out of order. So I can't apply this pair constructor to the second component without first giving the first argument. So there is no type level flip function. I mean, for normal function, I could do it. I mean, instead of writing this explicitly, I could do fmap prime is flip, something like flip. Sorry, no, it's not the same. But with the swap, I mean, I could do something like swap fmap swap. Should work, I think. Does that? Maybe not. Not really sure why not. Bit confused right now, but sorry, F. So, but something like that, unfortunately, I can't do on the type level. So, I mean, I could try to do something like this. So I could define a type synonym capital flip, FAB, which applies this thing to the arguments with the orders reversed. So I mean, that I can define. Type flip FAB is FBA. And so now, for example, I could say example 4 flip in bool. I could say example 4 is true. Did I say in pool? And now I could say true 42. So this is fine. And I can also ask for the kind of flip. So flip takes something of kind star to star to star, the F, and then two things of kind star, the A and the B, and gives me something of kind star. So far, so good. But I can't now, I mean, if I want this fmap prime, then I would like to write this. So I would like a functor instance on flip, comma, t, so that now the second component is fixed and the first is variable, and then define my fmap fmap prime, but that does not work. I mean, we can try it out. So we could try instance functor flip, comma, t, where fmap equals fmap prime. Then we already see that there's a red squiggle. And I think this is actually a different error first. So if I try this, let me try what happens if I activate all these extensions. Right. But now I get the error message that I can't get away from, no matter how many extensions I activate. That flip should have 3 arguments, but has been given 2. So we have talked a lot about currying, and it's perfectly fine to, if we have a higher order function like plus, I mean, it's perfectly fine to write something like plus 3. So even though plus expects 2 arguments, we can just give it 1, and then we are left, I mean, we have saturated 1, and we are left from a function from int to int. So we talked about that in the first week of the class. So that's perfectly fine. But now we try something similar with flip, which takes 3 arguments, and we only provide 2, the f and the a. And now we get this error here that it should have 3 arguments, but has been given 2. So for type synonyms, it's not allowed to, I mean, you always have to give all arguments. And therefore, we can't make this work. And the reasoning is somehow, I mean, you can't, because, I mean, the slides is not very satisfying, I think. It just says it would make it much more harder if that was allowed, would make the job of the compiler harder. So you can't do that. So that means order matters somehow. I mean, for functions, it doesn't matter so much. If we have a helper function and now we would like the arguments in a different order, I mean, we can do that with flip or something like this. But for types, there's not much you can do if the argument's in the wrong order. And that means that people often think very hard about, I mean, if you have a type constructor with several arguments, then the order really matters. So you somehow have to cleverly arrange them so that you have them in the right order to do what you want to do. So it's easy to give a functor instance for the second component of a pair, but not for the first component. Okay, are there any questions to this? Because that would now have been what I wanted to say about kinds. So as I said, normally you don't have to worry too much about them because you never have to explicitly deal with them. The compiler always takes care of it. But it's nevertheless good to know and to understand why, for example, something like undefined maybe or maybe IO doesn't work. But if there are no questions, then
Not so far.
okay, then we can continue. Let me just maybe comment this because otherwise it doesn't compile. Right, so now a different topic. So this was very theoretical. Now it's more concrete, persistent data structures. And I mean, this is not really any language, but I mean, we saw that, I mean, if we have something like a dictionary or associative map, like our table example, then in imperative language, if you wanted to insert like key 42 value bar, then you would normally like change the dictionary in place. So if you have a Python map or something and you insert new key and value, then the map would be modified in place. Whereas we have seen in Haskell, we leave the old map alone or the old table alone, and our insert results in a new updated table. And so in imperative, we do so-called destructive updates. So we destroy the old value and modify it in place. And in functional style, what we have done now in the last weeks, we create a new value and leave the old one alone. And typically in imperative languages, many operations make use of these destructive updates. And after you do such an update, the old version of the value is no longer available. There are exceptions, of course. I mean, in my, like in a previous life, I've worked with C#, for example, and I know in the later versions of C#, they also had libraries for persistent data structures. And of course, in Haskell, as we saw with IO_ref, for example, we also can do these destructive updates. But nevertheless, it's not the default. And in imperative languages, normally these destructive updates are the default, as in Haskell, to not do that is the default. So most operations create a new data structure and the old versions are still available. And data structures that work like this, where the old versions are always still available, are called persistent. And as I said, by default in functional languages, and in particular in Haskell, most data structures are automatically persistent. And in imperative languages, most data structures are not persistent. So the opposite word is ephemeral. And of course, as I also said, normally you can use ephemeral data structures in functional languages, and you can also use persistent data structures in imperative languages. I mean, an example in Haskell would be IO_ref, which is ephemeral because we can modify the value that's saved at this IO reference. And the question, of course, is how does that work? Because it sounds, when you first hear about it, it sounds horribly inefficient. I mean, if you think you have a very long list, for example, with thousands of elements, and now you want to insert an element, if you then basically had to copy the whole list to keep the old, to persist the old value, if you had to copy the whole list and then get a new list, that would be horribly inefficient. So let's look at lists, how that actually is represented in Haskell in memory. So if you have a list of 4 ints, for example, as we already know, this is just syntactic sugar for this. And in memory, it basically looks like this. So we have a memory cell that contains this colon, and then 2 pointers, one to the head and one to the tail. The tail is again a cons, so-called cons cell, pointer to its head, the 2, and so on. And the last one, this colon here, has 2 pointers. The head is 4, and the tail is the empty list, nil, where it ends. So far, so good. And if we now do this, so X is this list, and we set, and Y is the list with 0 const to X. And then let's say we want to drop 3 elements of this. So what does that look like? So first the Y. So we don't copy anything. So the X just stays as it is in memory. And to construct the Y, we just construct this new const cell colon where the new head is now 0. And the tail just points to the old X. So we don't need to modify anything or to copy anything. So we just create basically this new thing in memory and let the pointer here, the tail pointer, point to the original list. And if we now want to drop 3 elements, then Z also doesn't copy anything. It just points to the right spot. So the 0, the 1, and the 2 are dropped, and the Z points to this const cell. And in imperative languages, if you did something like this, you would have to be very careful because in an imperative language, you would be able to, like, in place modify, for example, turn the 3 into a 30. And if you did that, then automatically the Y and the Z would also have that 30 now suddenly. So that's, I think, sometimes called aliasing, or I'm not sure. But that's a danger. But in Haskell, you can't do that. So in Haskell, everything is fine. You can't modify these elements anyway, and therefore this is perfectly safe to do it. So, like, Haskell always tries so that values share data basically. And because everything is immutable and you can't change it, that's perfectly fine. So you don't make any errors doing that. And that's also why it's not horribly inefficient and why it can be very fast. So if you just cons 0 to a list, you don't have to copy this whole list somewhere in memory and then put the 0 in front. You just have to do this here. And same for drop. The old list just stays and you just basically have the Z point to a different position in the original list. And now if you do something like take, this situation is different. So if you want to take the first two, that's a problem. I mean, if we had W point here, then it doesn't stop here at the 2. So then we really have, in that case, we really have to do something like this. So we can keep the 1 and the 2 itself. I mean, they could also, in this case, it's ints, but it could be much more complicated values. So it's still okay. It's still good that we don't have to duplicate the 1 or the 2. But we can't reuse these things because after the 1 and the 2, we need a pointer to the empty list. So take in that regard is basically less efficient. So, we always try to allocate as little as possible, but as much as necessary. So whenever it's possible to share something that already exists in memory, we do, but sometimes it's not possible, and then one has to create new things. So basically, instead of, nothing gets modified, everything is immutable. And if we do something like inserting into a table or a list, that happens by creating new node and pointers. Sometimes we have to copy something, but we can never modify anything in place. So if we want to copy as little as possible, obviously, and reuse as much as possible, which is good for like memory and for speed. And this is, I think, not very important, but basically internally, values are represented using words in memory, obviously. And normally the first word is a tag that identifies the constructor. So, typically we have these algebraic data types which can have one or more constructors. So the first word in memory is normally used to identify the constructor. And then the other words are the payload. So basically pointing to the arguments of the constructor. And as I also briefly mentioned last week, when somebody asked, so there are these, because Haskell is lazy, stuff is not eagerly evaluated, only when needed. So sometimes these pointers point to to some code. So if somebody actually needs the value, then these so-called chunks get evaluated and then cached. So they only need to get evaluated once. Right. Are there any questions here?
Nope. Oh, wait a
No.
minute.
Yeah.
So a list is internally represented as a tree?
If you want to call it that, yeah. Like a degenerate tree.
Yeah.
That's like very non-balanced tree. Yes.
I think that's it for now.
Okay. Everything is basically a tree, or actually, I think it could also be a graph rather. Sometimes you can have like cyclic data structures in Haskell as well. So it's not, everything in Haskell is basically a graph. We have pointers that point to memory cells, and those can again have pointers that point to memory cells and so on. You can have something and something like, let me see whether I get this right. Yeah, you can have something like some 5. Sorry, a list of whatever, int or character, it doesn't matter. Can do something like this. Sorry, character I said. So this is completely legal Haskell. And it's also, I can, for example, take 20 of x5, and then I get 20 x's. And this will in memory actually be represented, I mean, not as a tree, but as like a cyclic thing. So if we go back here, no, let's go back here. So then it would look like, so the colon, then the x, but then this pointer would point back to itself. So it wouldn't be a tree, it would be even a cyclic graph, not even an acyclic graph, it would be, or acyclic graph, it would be a cyclic graph. So there can be cycles in Haskell values. So yeah, it would look like this. So colon, then one arrow to the x, and the other arrow would cycle back to the thing itself. And this is now actually a little bit of a pity. So the next, the next chapter is actually about visualization tools. But unfortunately, this is all a bit outdated, and those tools are not really supported anymore, or not well. So it's I didn't get that to work, unfortunately. So there are tools where you can basically get these pictures that I showed you of your own data structures to inspect it. And here in the slides, there are some tools, but I try to get this GHC Viz for visualization to work,
Yeah.
but I didn't manage to.
Meaning it's like stuck in 8.8, and I cannot run it in my computer either.
Right, so that's a bit of a pity. And then you would get like images like this.
I mean, if just to showcase the images, maybe we can in the documentation there's a bunch of examples of how it will look like, but not like in.
Right, right. What I did actually get to work was this GHD heap view, but that is like not graphical, so it's also maybe not very pretty. Um, but that's much lighter. I mean, that easily compiles. But as I said, it's not maybe not very enlightening.
Maybe at some point we can create like a separate environment just for
Hmm.
this, because there's no way we can match our updated environment with the old one needed for these visualization tools.
Right. Yes, I also think it's not very important. I mean, I've personally never felt the need to use that, but maybe it might be helpful, of course, to play around with it a bit and see how that looks like. So then you would get something like this, and yeah, okay. So yeah, it's just, I mean, it's also of course not important to know how that actually looks in memory or how Haskell maps that in memory. The important lesson is that one doesn't have to be scared to use these. I mean, one doesn't have to worry that Haskell is horribly slow just because it makes it generates new values instead of modifying in place. So that doesn't mean that it's slower than Java or imperative languages, not necessarily. Of course, it depends on, I mean, you must use good data structures that are actually suited for the job at hand. And that's basically what we come to next. So trees, they are normally really useful for functional programming and for persistent data structures. I mean, the trees, I mean, they come in all sorts of shapes and colors. I mean, we have had our running example of these simple binary trees, but we also saw rows trees in the assignment. Sorry, in the test. And yeah, I mean, lots of things are trees in Haskell, and they somehow fit nicely with how we write recursive functions. So, I mean, we saw lots of examples of writing recursive functions on trees. Normally, that aligns very nicely. So, this recursive data type with the recursive functions. And it's easy to do what I showed you for lists. I mean, to reuse parts of a tree when you like create new trees. That's relatively easy to do with trees. So because most operations on trees only affect one path from the node of the tree from the root of the tree to some leaf. for example, if you insert into a binary search tree, then you, I mean, follow this path down the tree until you find the spot where you want to insert, and then you insert. And that means that basically most parts of the tree can be reused for the resulting tree. And only along this path do you basically have to create something new. And basically everything is a tree, or most things are trees in some sense. I mean, not necessarily binary trees, but most things are tree shaped in Haskell. I mean, as somebody asked before, I mean, even a list is a tree, just one that's extremely unbalanced because it's like right leaning. But you could think of it as a tree. Right. So now we want to look a bit at like performance characteristics of lists, and then also at alternative to lists. I mean, lists, we use lists all the time, and somehow, I mean, the syntax, Haskell has special syntax for lists, as we have seen, so we don't have to write this 1 colon 2 colon 3 colon empty list. We have the special syntax with the square brackets. We have list comprehension. So lists are like the working horse of Haskell or functional programming. So similar to how arrays are used everywhere in like imperative languages, lists are basically the default data structure used in functional programming. However, they are for a lot of things not very efficient. So if we have a list of operations on lists, so empty list, appending or prepending an element to a list, this colon, head of the list, tail of a list. Snog is like adding element at the end of a list, so it's cons written backwards. Indexing, getting, I mean, random access, basically getting the nth element of a list. Concatenating lists, reversing lists, splitting a list into two parts at an index. Union, I mean, we haven't seen that explicitly, I think, but I think it's in data.list. So given two lists, get a list of all the elements, but without repetition. And lm, checking whether a given element is an element of a list. Then, I mean, the empty list is constant time operation. Consing is constant time operation. Head and tail are constant time operations. Snog is horrible because you have to traverse the whole list to get to the end to append that element. Indexing is O of n because you have to again traverse the whole list until you get to the right index. Concatenation is okayish. It's O of the length of the first list, but still, I mean, not wonderful. Reverse is O of n, but only if you're careful. I mean, we saw if you do the naive reverse, then it's quadratic runtime. But if you do use the fold left prime version, then it's linear. Splitting is O of n, basically same as indexing. I mean, you first have to find the position where you want to split. Union is horrible. It's basically quadratic. So order of the length of the first list times order of the length of the last list. Because in principle, you have to compare every element with any other element for equality. And lm is again linear because you have to go through the whole list to check whether an element is in there. So that means lists are really only efficient for these things here. And if we want to do operations like this, then they are not. So so what is efficient is operations that are basically busy with the head of the list. So I mean, prepending an element front of the list or looking up the first element of the list and so on. And that's what is called here on the slide stack operation. So if you think of a list as a stack of cards, for example, where the end of the list is at the table and then the head of the list is on top, then as long as you operate basically only with the top of the list, like put things on the stack or remove things from the top, then it's fine. That's very fast. But if you have to like get to the bottom of the list, then it's inefficient. So if you are mostly doing the stack operations, it's fine. And if the length of the list is somehow bounded, I mean, if you know that our lists are never longer than whatever 10 elements or even 100 elements, then it's fine. But it's not okay if they can become very long, and then we have to do non-stack operations. Right. So traversing a list, I mean, if you have to do it anyway, for example, if you have to do the sum of all elements, then list is also fine, because obviously in order to do the sum, you need to look at at each element. So you can't expect anything better than linear performance. But lists are really bad for random access. So if you want to efficiently get to the nth element of a list, or for set operations like union or intersection, or to deal with large amounts of text via string. That's something I've also mentioned before, briefly, I think, that if you really want to work with text, I mean, not just with like simple words or sentences, but really large bodies of text, then string is quite inefficient. And there are much better choices in the Haskell libraries than the string type. String is just nice because it's conceptually so simple. It's just a list of characters. Okay, and then of course the question is, so are we doomed if we want to do anything like this, like random access, or do we then need to go back to Java or C++? And of course, the good news is there are functional data structures that support these other operations that are not so wonderful here. There are purely functional persistent data structures that have much better efficiency for operations like this, and that are not lists. And one is so-called balanced search trees. I don't know, I mean, not really sure how many of your assignments you have already done. I know that one of the assignments from the first week actually deals with binary search trees. So it's like our tree type more or less, but at each node there is a value, like a key, and then they have this search tree property that all the keys in the left child are smaller than the value, and all the keys in the right child are larger than the value. So I hope most of you have at least seen this exercise. And those are in principle good. So they are efficient because the size of, I mean, basically the runtime to do things on a search tree, roughly speaking, depends on the height of the tree, how far you have to go down from the root. And ideally, that's like logarithmic in the size of the tree. So yeah, so that's actually very good, would be very good. The only problem is that search trees can degenerate. I mean, if you are not careful, they can look like lists in the end. So where it's not evenly distributed, the leaves on the left and right hand side of the tree, but everything is dangling on the right, or everything, or most of everything is dangling on the left. And if that happens, then basically the runtimes degenerate to performance of lists again. And that's where this balancing comes in. So any of you that has studied computer science or done at least some course on data structures or so, I'm sure you have encountered balanced trees. So I don't know, there are red, black trees, and I mean, that's the one I know. There are all sorts of like balancing schemes to some ideas. So the idea is to sort of keep your search trees balanced. And if they become imbalanced, then you do something to rebalance them. And that can actually be used to implement finite maps and sets efficiently and persistently. And I'm sure I've mentioned the library before, even though we haven't looked at it in detail. So in Haskell, that's in the containers package. And there are types, particular data.map, data.intMap, that have basically the same interface as our table that we looked at in the first or second lecture. But instead of just using lists of pairs as we did for our table, uses these balanced search trees. So maybe I should show you on Hackage. So if we do containers package. I think we looked at that before, but let's look again. So that's not part of the base library, but it's, I don't know. I mean, it's very important. So virtually every serious Haskell project uses containers as a dependency, and they have like lots of stuff, but in particular they have this data.map, data and data.set for maps and sets. Inset or intmap and inset is specialized maps where the keys are ints. So it seems in that special case, if you have int keys, you can have a more performance special implementation. And then if we, for example, look at data.map, then we don't see much because I think most of the implementations are here. Right. And there we have all sorts of operations that we would expect, like empty, what we also had for our table. Construct an empty map, then insert into a map and look up. So it's really the delete and so on. And it's all this this functional style. So delete doesn't delete a key from a map in place. It gives you a new map with the key deleted. Maybe I should play around a bit with this just to, because it's so important and it's used all over the place. Remove this. So you would then say that you depend on containers. Just reload it. And as I am sure I already mentioned, there's a lot of clash of names with stuff in the base libraries. So the way one normally imports this is you only import the map type itself directly and the rest of the library qualified. I always call it map. You can also call it M or whatever. Okay, and then now we can, for example, start with something like, I mean, the empty, say map, I don't know, string int. Okay, and because of the qualified thing, I have to qualify it. Right. Now I could, for example, insert something, map insert Haskell 5000 and map insert, no, Java minus 9990, Java. And we can also see what happens if I insert something again, a key that already existed. So in our table implementation, we just shadowed the old value, but left the old value in there. Here, we don't. Delete. And look up. Why not? Ah, the type is wrong now, of course. That's now of type maybe int. Right. So yeah, that's exactly the same interface that we had for our table type, but it's much more efficient. Sets as well. So you would import sets like so. Now we can have something, so let's say a set of strings. can insert. And of course, I mean, it's called set because it takes care of duplicates. So if I insert Java again, it's still there only once. And so on. I mean, now I can ask, for example, member JavaScript set member, which is false, but member Java 2. Right. So there, I mean, that's very common to use those. They are basically, I mean, they are very universally applicable for lots of applications. They are actually beautiful data structures that are suitable for lots of scenarios. And as I already like verbally described, so they are actually implemented as under the hood. I mean, it's opaque. You as user of the containers library don't have to worry about how they're implemented, but internally they are implemented as binary search trees. So, and the keys, if you look at here, whatever, insert, for example, there's always this OR constraint on the keys. That's a disadvantage to our simple table implementation. There we only needed eq in order to support deleting, but we didn't need org. But because it's done as a binary search tree, you need this OR constraint because you need to order the keys for it to work. So the keys are ordered, and that enables efficient lookup. So therefore the keys need to be ordered. And as I mentioned before, so how it works is normally you just insert like naively, like you would in any binary search tree. But if by doing so the tree becomes imbalanced, then so-called rotation is done. It's like tree surgery, where some subtrees like shifted around to rebalance the tree, and that guarantees that the operations remain sufficient. And everything is persistent, so we keep old versions around and don't always copy everything if we create a new version. And sets, you can think of them as basically just maps where we are not interested in the value. So the value is always unit. And then, as I already mentioned, there are these specialized implementations for int keys. And if we now look at the performance, that is, I mean, looks very good. So empty, of course, is constant time, but insert, lookup, delete, update, they are all logarithmic time, which is very good. I mean, that's almost as good as if it was constant time. And okay, union is also much cheaper than, if you remember with lists, it was m times n. So here it's m plus n, which is much better, of course. And here checking whether a key is a member or the size, or actually also the map operator. I mean, map is not surprising, that's O of n. But member is also logarithmic. So basically everything is logarithmic, which, as I said, in practice is just as good normally as constant time, because the logarithm function grows so slowly. So this is really a very useful data structure. I mean, for a time, like 10 years ago or so, I wanted to practice my Haskell skills to get it into muscle memory, basically. So I did a lot of these hacker rank competitive programming things, and where, of course, most people use C++ or something and then arrays. And I almost always got away with just using maps for everything. So instead of arrays, I just use maps. I mean, there are some like specialized scenarios where map is not good enough and you need something more clever. But map is like in, I would say 90% or 95% of cases, map is just good enough. It's a very useful, very versatile data structure. Maybe briefly look at the implementation. That's not so important, but just so it really is basically a tree type. So tip is like a leaf, but it doesn't carry data, or it's a node, which is called bin for binary, I suppose, which basically recursively has a left child and a right child and a key and a value. And for performance reasons, it also remembers the size of the tree. And this unpack is something we haven't seen before. That's a pragma, which basically tells it that the size will be like directly there in memory in int. So no level of indirection, no pointer to a thunk or something. So this is just for performance reasons in there. So it's either a map is either empty, it's a tip, or it's a binary node called bin. And this bin then contains the size of the tree, the key value pair, left and right subtrees. And right, I mean, I'm not so sure this is important to look at that, but I mean, just as an idea, so basically the empty tree would just be tip, singleton tree just or map just containing one key value pair would just be a bin with two empty left and right children and just a given key and value in the node directly. I come to this small b. I mean, the constructor is a capital B. This is not a typo that it's small b here. And this is something that's often useful. That's like a functional programming pattern, so-called smart constructors. So in this case, I mean, if we look back at the constructor, we would need to also provide the size of the tree. But that, of course, is room for error because we could make a mistake. I mean, the size is, of course, just the size of the left subtree plus the size of the right subtree plus 1. But one could make a mistake there. And therefore, this is right. So this is basically taken care of by this so-called smart constructor. So it uses the real constructor, but it automatically computes the size. So the user doesn't have to worry about that. So it's smart in that sense. Right, and the implementation is simple. So tip has size 0, and of a bin, we just read this value. The size is explicitly given as one of the constructor arguments, so we can just read it off. Right, and then by not using the constructor directly, but instead using this smart constructor, we can't make a mistake with the size because this bin, lowercase bin, automatically takes care of that to calculate that for us. I mean, this is not only an example. Smart constructors can often be useful, especially for something like that when you want to like preserve invariance like that the size is correct. And I mean, lookup. I mean, for those of you who have done the exercise for the binary search trees, that should look very familiar. So you want to look up a given key in a map. So if it's the tip, then it's the empty map. So your key is not in there, so you return nothing. If on the other hand, it's a bin, then you compare the key you are looking for with the key here, this kx. And if they are equal, then you have found your value. It's just x. And if not, then you must look into the left or right subtree depending on the key you're looking for is smaller or larger than the kx. Okay, I think we have seen all of that. And then finally the insert. And if we didn't have to worry about balancing, that would be fine. I mean, that was also in this assignment from the first week with binary search trees. So if you insert into a tip, you just basically do singleton that we saw before. And if you insert into a node, then you must compare the key you want to insert with the key at the node. And then depending on whether it's, I mean, if it's smaller, then you recurse into the left subtree. If it's larger, you recurse into the right subtree. And if they're equal, you keep the left and right subtree and just change this value here. And the new thing, or what makes it slightly more complicated, is that now we have this balance here. So the idea is that if by inserting this, your tree becomes too unbalanced, then this balance will rebalance it. And I think it makes no sense to go about that in detail. So you could just ignore the balancing and just use bin instead of balance, which has the same signature. But then you would risk getting imbalanced tree. But I think just want to show you the picture, so it doesn't really matter. I mean, it's complicated. So the idea is basically just if you, this tree, for example, has become too heavy on the right, and then you can do this so-called tree rotation, which is graphically visualized here. And I think it's really not important to basically understand the details. The point is it basically preserves the order of the keys, so it's afterwards it's still a search tree, but afterwards it's more balanced than it was before. So you sort of rotate the subtrees somehow to the left so that the stuff which is very far down here gets heaved up and this part is lowered down a bit, and then it's balanced again. And then there's also like something on the other side. I mean, to turn it the other way around if the left side becomes too heavy. And okay, the slides claim it's easy to see all of this. And actually, it's true. I mean, it's actually easier to implement this than, you also get balanced search trees, of course, in traditional imperative programming. And then trees are normally done with pointers and you have to like manipulate lots of pointers and that can get really messy. So if any of you ever had to do that at university or so to do tree balancing, then you can probably appreciate that this here is much simpler. I still find it a bit icky, but nevertheless. Right. And I think if there are any questions, otherwise we could have a short break now, I think.
No questions.
Okay, then maybe, I don't know, until like 10 to 4 or something. Like 10 minutes and a bit.
Sure, 10 minutes.
10 minutes, yeah. Okay, then I talk to you in 10 minutes. Okay, welcome back. Can we start again?
Yes.
Okay. Right. So there's another module in this containers package called sequence, and that's also a very nice data type with very nice characteristics, which you can often use where in imperative languages you would use arrays. So sometimes we need something array-like where you have efficient random access to arbitrary elements. So you can say you want to look at the 3567th element or change it, and where you have efficient access to both ends, not just the head, like in the stack-based list type, and where you can efficiently concatenate and split, so where it's not linear like for lists. So that's often useful to have something like that. And the data sequence library provides just that. And if we look at the characteristics here, so it's, empty is constant. This is basically cons for sequences. So that's constant time. This is SNOC, which for lists was linear. It's also constant. Concatenation, which for lists was linear in the length of the first list. Here is logarithm of the minimum length of m and n, so logarithm, much better. Check whether it's the empty sequence or the length is constant time. Filter and fmap is still linear. You can't really expect any better because, of course, you have to look at every element to do this. But in particular, indexing, so random access, looking at a specific index, but what it lists is O of n is here again logarithmic, and splitting is also logarithmic. So it's much better performance than lists for these operations. So whenever you need something array-like like this, you should reach for this sequence type seek, which is in the containers library. And they are actually implemented as something called finger trees, which is a fascinating data structure. So sequences is only one example of that. Maybe we should, for those of you who have like theoretical aspirations, there is a beautiful paper by Ralf Hinze, I think, called Finger Trees. Maybe we could leave a link on the GitHub, where it's basically explained what all they can do, and they can do all sorts of cool things. But for the purpose of this lecture, again, if you want to use the sequence library, you don't need to know how they're implemented, but actually they have something interesting that we haven't seen before. So they use this finger tree A type, which is again a tree. So it can be empty, it can be a single A, or it can be deep. And this looks sort of familiar. So left subtree, right sub something. But this is interesting. So it's a recursive data type. So we define finger tree, and somewhere here in the deep constructor, there's again finger tree. But now there's something we have never seen before. In our examples of recursive data types, for example, lists, there was the second constructor cons, which takes an A and again a list of A's, the tail. Or if we think of our tree type, maybe I can just repeat the tree type and the list. Of course, it's silly, but lists are built in, but I can define my own list type. So that would be nil or cons A list A. Or our tree type was leaf A or node tree A, tree A. So those were two example recursive data structures that we have used a lot as examples. And if you look at so they're both recursive because we are defining list of A's. And here in this case, in the second constructor, second argument again mentions lists of A's. Same for tree. We are defining trees, and in the node constructor, the arguments are again trees. So that's what makes them recursive. Note, however, that we are defining list of A's, and the recursive argument is again of the same type, list of A's. Same for tree. We're defining tree A's, and the recursive arguments here to the constructor are again of that type, tree A. But if I now go back to the slide where we define finger tree A, it's not finger tree A here, it's finger tree node of A. So it's a recursive call or a recursive mention of the same data type, but we change the argument. So it's not A, it's node A. So that's something that's allowed in Haskell, but we haven't seen it before. And the digit and node types are defined here. So a node A is basically 2 A's or 3 A's. And the digit A is 1A, 2A's, 3A's, or 4A's. I mean, the details again don't matter. The interesting thing here is that finger tree A recursively in this constructor, in the deep constructor, has a finger tree, but not of A's, but of node A's. Right, and again, there's like stuff to make it efficient. I think we really don't have to look at the details. Just basically to give you the rough idea that how this works, that access to like the beginning and the end of a sequence is so efficient, because here in the deep constructor we have them like lying around. So this is basically the beginning of the sequence. So it's at least 1A, 1 to 4A's. This is the end of the sequence, 1 to 4A's. And this is all the rest stuff. And this, as I said, we haven't seen before, recursive, where the argument is different to what we're defining. That has a name, and it's called a nested data type. And so now we want to look at nested data types as an example. So this is now much more practical, and it's actually quite cool. Sorry, so I showed you this already. And now let's look at this perfect tree type. So let me define this. So an example is simple, much simpler than finger trees. Let's define this perfect type. And before I do that, I mean, if we look at our tree type, so it's binary trees. But we can, of course, have something like right. So let me just remark. So binary tree is called perfect if all its leaves have the same height. I'm not sure whether height, no, height is maybe, let's say distance to the root. So for example, I don't know, it's always difficult to do this ASCII art thing, but for example, node, leaf 1, leaf 2, node, leaf 3, leaf 4 is perfect. So all these leaves, the 4 leaves, there, I mean, it's, I don't know whether one should. Draw a picture. It's always a bit difficult to do this in text. Oh, why is this happening to me? So this is now not Picasso, but I mean, it looks something like this. Maybe. I suppose. Yeah, looks about right. So, I mean, basically, it's completely symmetrical. So right. And all the leaves are basically at the same level at the bottom. And an example for a non-perfect tree would be node, leaf 1, node, leaf 2, leaf 3. It's not perfect. So there the picture would be something like 1. Drives me insane. Like so. So it's, I mean, perfect as in perfectly balanced. So this one is perfectly balanced and this one is not. I mean, it's heavier on the right side than on the left side. Right. And the point is, can we define a data type of perfect binary trees? So the question is, I mean, with this type, as we see in the second example, I can write down a value that's not perfect. I can, of course, also write down a value that is perfect, but nothing stops me from defining trees that are not perfectly balanced. So, and it might seem impossible, or at least very difficult, to basically write down a type where you only can define perfect trees, where it's impossible to write an imperfect tree. But you actually can, using nested data types, which I think is a very pretty example of the power of functional, purely functional data types, data structures. So one way to do this is define type of perfect binary trees with data A as with two constructors. One we call, let me just use the same notation as here. One we call 0 that takes an A, or for some reason, normally I think it should be two C's, but whatever. Perfect A, comma A. Let me do deriving show. Right. And after what I've said earlier, so this is an example of, again, of a nested recursive type. So the perfect that we are defining appears in the definition itself on the right-hand side in the second constructor, but with a different argument. So we are defining perfect A's, but we are defining them by using perfect A, comma A's. So just to get you a feeling how that works. So let's define a couple. So tree 1, say tree 2, 3, 3. Not sure how far I want to go, maybe to 4. Let's say perfect ints. So tree 1, the simplest one by using the 0 constructor. So now I need one int. So for example, 1. Now tree 2, if I use the suck constructor once, so now I need as argument a perfect tree with int, comma ints. So let's say 0, 1, comma 2. Tree 3, let's use the suck constructor twice. So now I need a perfect tree of pairs of int, comma int, comma int, comma int to make the compiler happy. And finally, if I use suck 3 times, now I need pairs of pairs of pairs of ints, I think. 2, 4. 6, 8. Now I probably got some parentheses wrong somewhere. Okay. Okay. Not okay. This was also already wrong. This one is still good. Okay. Why is this now complaining? You just see whether 2, 3, it's still good. Seems to be. No. No.
I think you might missing a parenthesis at the end. Yeah, there.
Yes. Okay. Now this is correct. Sorry. Let me just get the first 3 right. There's something wrong already. Whatever that may be. Looks good. Why the?
Can you hover to see?
Yeah, just 1 second. I forgot. I forgot the 0.
Ah,
Okay, this is correct now. Okay. Here as well, I forgot the 0 constructor name. Not now. Oh, it's probably one.
I think you're still missing a parenthesis at the end of 3.
Uh-huh. Okay. Oh, yes.
There.
Yes, yes. Okay, thank you. Anyway, so right. So I hope you see how that works. So I mean, each time I start with ints, then if I use one suck, then I need int comma int, and each time each suck I need more. Basically, what I have gets doubled. So I always have a power of 2 of ints. So I have 1 int, 2, 4, 8, 16, 32, 64, and so on. So it's always perfect. I mean, if you visualize this as a tree. So yeah, I think this is very cool that you can do something like that in Haskell. There's an article that I once read. I mean, you can do this. I mean, this is maybe not extremely useful, this one here. But for example, for square matrices, you can do something similar, that you can basically enforce that the matrix is square just on the type level. So far, so good. That's cute. However, it's relatively difficult or not as easy as we are used to actually work with these trees. So let's say we want to write a function that sums all the values in a tree. So let's say we want to have something like sum tree. Let me just check what it's called here. Right. This slide, just the last point, just that these finger trees also use something similar. Yeah, whatever. So did this, did this, did this, did that, did even one more. Okay, sum perfect. So let's say we want to define this. And this is actually more tricky than one should think. So let's try this. I mean, of course, we know that how to write functions on algebraic data types by following the type. So one equation per constructor. So let's start with the 0 constructor. So in this case, it's a tree that only has a single leaf of type int. And then the sum, of course, is n. So this is good. Except that I need parentheses, of course. So far, so good. But now for the recursive case. So we have suck and now a different, I mean, a tree, whatever t. So now what? I mean, now I would like to somehow recursively call some perfect on T. I mean, that's what we always do, right? If we always observed if we have a recursive data type and then we define a function on the data type following the standard pattern, one equation per constructor, then we observe that we normally have like recursive calls if the data type is recursive. So we expect that we need a recursive call to some perfect. But I mean, if I write some perfect T here, for example, then everything is red. Oh, sorry. This was, of course, also in parentheses. So it's one of the reasons everything was red. But nevertheless, of course, now the types don't match because I'm defining a function from some perfect into int, but now the T is not of type perfect int, it's of type perfect int, comma int. So I can't recursively call it with T. So this doesn't work. So somehow, I mean, I need this some perfect. If I want to make a recursive call, I somehow need it for more general types. Now the second idea might be that I, instead of for int, I just do it for arbitrary a's, let's say, or sorry, for arbitrary a's. So in this case, I mean, this recursive call would be fine, but now the base case doesn't work anymore because if it's for arbitrary a's, then I can't say the sum is n because n is now an arbitrary a, not necessarily an int. So that unfortunately also doesn't work. And now the trick is to make it even more general and say, okay, the problem here is that I have some arbitrary a and I don't know how to convert that to an int. But if I just taking an additional argument that tells me how to convert an a to an int. Okay, then I can, so I have this function, this additional function. Now I can, in the base case, I can use it and apply it to a. So the base case is good, provided I know how to convert an a to an int. I can apply this function f to the one a I have here, and I'm good. I get an int. Now in the recursive case, I need to do something here. And let me see whether the compiler can help me actually. Not really. We come to that in a second, but the compiler has problems with nested data types. But let's see. I mean, the T is now of type a comma a because of this here. So this must, whatever I put here, let's call it G. Must be now taken a comma a and converted to an int. Let me just put undefined here. And this is, of course, some perfect prime. Okay. There will be problems later, but for the second, let's ignore it. Right. And now, of course, what do I do here? Well, now I can use my original f. I mean, I know how to convert one a to an int. Now I have two a's, so what I can do is I can apply my f to both of them and then sum the results. No. Right. And now I get this weird error. And that is a problem with GHC. Actually, if you use the newest Haskell version, this GHC 2021 in the Cabal file, this wouldn't be happening. The problem is that GHC doesn't know that this A I'm mentioning here is the same as that A. So for GHC, they are completely different type variables. That's a bit annoying and often not what you want. But luckily, there's a way out. So that's an extension that is almost always useful to have. It's called scoped type variables. And the only other annoying thing is for it to work, although for some reason I don't have to, I do. You have to write you must explicitly say for all A. Normally, we never have to write that. That's always, I mean, the compiler understands it automatically. If we mention a type variable here, have a polymorphic function, we know what that's supposed to mean is for all possible A's, blah, blah. But for these scope type variables to work, one has to explicitly write for all A. And if you have more than one type variable, then you would mention all of them. So for example, the swap that I defined earlier as an example, equivalently, I could also say for all A, B. So it's just more verbose. But if you use these scope type variables, then you have to mention that there. So that's all a bit annoying, but now it basically understands that this A is that A, and now this compiles. So we can try it out. And okay, this is sum perfect prime. Now but we want our sum perfect, but this is now easy to define. I mean, the original one, which works on perfect ints. So we just use this helper function that we just defined. And now we need a function from int to int. So we just use the identity function and we are good. So let's try it out. Sum perfect 3, 1, 1, 2, 3, 4. So I hope that's correct, but I think it is. Right. And so yeah, this is a bit tricky. But this example is also quite typical. So we will have assignments for that when we eventually come to the assignments for the lectures for this lecture. And but this basically is often like you have to do it, like have this somehow helper function. And one other interesting thing to observe or to note is if I comment the type signature here and reload, why is this happening to me? Because that's not supposed to work. Interesting. Just a second. What happens if I remove this? Now I'm a bit confused because according, sorry, yeah.
Maybe just because of having the extension activated, it's already understand.
Yeah. I think that's a new. Okay, fine. I remove that again.
It works.
Maybe that must be a new thing then in GHC because that didn't used to work. That's interesting. Okay. Nevertheless, I mean, I do want this type signature, but because if you look at the slides now, sorry for the confusion, but I think I did it basically. I mean, I named it differently, but I did it exactly like here.
Yeah.
I just didn't call it new K, I called it G.
Mm-hmm.
And then, okay. Oh, no, sorry. Sorry. This one, if I omit this one here, then it doesn't compile. So all good. Right. Sorry. Everything good, nothing new in GHC, all good. It was the wrong type signature that I omitted. So I can do this back. Hey, okay. Sorry. Right. Which is interesting because when we talked about type inference and GHC, then we said you never have to explicitly annotate types, or basically never, because I mean the type system GHC uses is cleverly designed such that inference is always possible. So there's an algorithm that always allows GHC to figure out the most general type, and you never need type signatures. That's one of the big advantages of the specific type system that Haskell uses. But that is no longer true if you use nested recursion, nested data types. So then type checker can still check that the type is correct, but it can't infer it anymore. So you basically have to help the compiler. So this is, you really need this type signature here for some perfect prime. Otherwise you get some weird error message that nobody can understand. Yeah, so nested types are somewhat tricky. And now why do I, because,
For all,
sorry, yes, for all. Right. So this is really, yeah. And I think it's also not extremely common in Haskell, so don't worry too much about it. It's more like a brain teaser. I mean, especially the assignments, some of them are really quite tricky. I think they are some of the most difficult assignments in the whole course. But for people who like puzzles and like brain teasers, it's very nice. I really enjoyed when I saw it the first time. Yeah, so this is a bit tricky, but it's very cool and very powerful that you can, on the type level, basically encode something like this, like the shape of the tree. And right, so that's nested data types for you, I think. So this is just says that can't. And as I said, so the data types that are recursive at the different types are called nested data types. So the analog for functions is they are called polymorphically recursive. So if you call if a function calls itself, it's a recursive function. But if it calls itself at a different data type, like in our case, then it's called polymorphically recursive. So this is the case here, right? We call the function we are defining, this some perfect prime. We call the same function, but at a different type. I mean, we start at A, but then we call it at A, comma A, pairs of A and A. So that's a polymorphically recursive function. And then this, I mean, the type system Haskell uses, at least in its without extensions, is called Damas Hindley Milner type system. And that has this type inference, the algorithm that automatically, without type annotations, can figure out types of your programs or your expressions. But it can't infer polymorphically recursive types. So for those, you do need explicit type signatures. And in the same way as we saw that functions on normal recursive data types are normally recursive, functions on nested recursive data types are normally polymorphically recursive. So there's again this correspondence between functions and types. So they are not as easy to work with as other, like more vanilla algebraic data types. But on the other hand, they are also, I mean, they are quite powerful. And right, so the summary is to keep in mind that we have persistent data structures, and that's the default for functional data structures. Then even though lists are basically pushed into your face when you do Haskell, because like in the prelude, the base libraries, there are lists all over and there's special syntax support for them, to not just always use lists. Sometimes or often there are better data structures for your needs. And like these general purpose ones like sets, maps, and sequences are really, really useful. So it's really very rare that you need something more than that. I mean, there are, as I said, there's this very famous book, Okazaki, Purely Functional Data Types, and there are really crazy data types in there that have like almost unbelievable performance characteristics. But it's very rare that you actually need something like that. So most of the time, especially for like your standard run-of-the-mill business application, maps and sequences are normally good enough. So they're really useful and really performant, and I think also highly optimized. Right. So that is the end of this lecture, and we still have like plenty of time, I think, 1.5 hours, right?
Yes, we can start with the second part, or maybe a
Actually,
break.
I mean, we just had a break, right?
Yeah.
I mean, like half an hour ago. I actually thought I can do my Monty Hall problem
Oh,
now.
nice.
I mean, it's like a reminder of monads. Another, I mean, a nice example of monads, and it's a bit more concrete and hopefully fun. And I
Yes.
mean, this lecture is very like dry, I think. So
Mhm.
maybe it would be nice to have something like that.
Yes. At least I would like to see it again.
Okay. So are there any questions?
Someone asked about the book, but I'm going to share a link briefly so you can keep going if you
Yes, right. You know that, right? It's called Purely Functional Data Structures.
Yeah.
It's quite old. It's from the 70s, I think. But it's, I mean, it's beautiful data structures in there. Very cool, actually. Right. So maybe I should create a new module in my Cabal file, because this is now a different topic. And I think I need random. And let's call it, probability. I mean, I must confess that's like a hobby of mine, probability stuff in Haskell. So I'm maybe biased, but I think it's very cool. Just let me just reload, because I think each time you fiddle with the Cabal file, it's a good idea in Visual Studio to reload. Let me open the REPL again. This new module. Okay, so first I want to like solve probability problems. So I want to do like stuff like throw dice or flip coins and I mean do some random experiment and somehow do that like in a Haskell program. And I want to show two approaches how one can do this. But first I want to, I mean, I want to basically be flexible in my approach. So I want to keep the way I write these probabilistic programs independent of how I actually handle this. And for that, I can show you a technique that's also, I mean, we will see that again in like next week. I don't know exactly which lecture. But so this is maybe like a preview to that, but it's actually a very simple idea. And it's also something that probably everybody of you that has some programming experience knows. It's basically this idea that I program against an interface and not against a concrete implementation. I mean, we have mentioned that before as well. So let me define a class, and I call it, let's call it monad prop. So I want to basically have a monad. So I have a superclass constraint that M is a monad. And then I say M is a monad prop where, and I only want one additional, so it's just, I don't care what monad it is must be a monad, so I can use do notation, for example. And I want one additional operation. I want to be able to flip a coin. Let me just call it coin. So given a double, which is the bias of the coin, I want an M bool. So maybe I should say coin P should, whatever, I call it, should represent flipping a coin with probability P for true and 1 minus P for false. Okay, so that's all I want. I mean, this is my abstract interface with which I want to do probability stuff. So just as an example, why this is useful to do it like this. I mean, now, I mean, just, we don't know what this monad M is. We just know it's a monad, and I have this special operation coin, which can do me a coin flip. So coin 0.5 would be a fair coin, Coin 1 would be one that always gives me true. Coin 0 would be one that always gives me false. That's the idea. And now just, I mean, but at the moment, I don't care how I actually implement this. I mean, what monad I could use. What is also often useful, I mean, this coin is a useful operation. It's also often useful, especially for this application I want to show you later, is to pick a random element from a list. And actually, we can do this now as a first example of something that lives in such a monad. So let's call it pick. So if I have such a monad prop, and I have a non-empty list, and now there's one problem. Yeah, that's always tricky. Let me just, it's a bit unpleasant. I mean, the problem is, how do you pick something from an empty list? And there are various ways now. I could say it's a maybe result, or I could say I just give an error. I don't know. So given a list of A's, I randomly pick one of them. So and now, and the problem now is I was now thinking, I mean, there are various ways to handle the empty list case. I mean, if I have an empty list, obviously I can't pick an element. So one way to fix that would be to do maybe A here. That's also annoying because then you always have this case distinction. One alternative would be to, instead of list of A, there's also a type actually in the container libraries here that's called, I think it's there. No, actually it's in the base libraries. Maybe that's a good idea. It's also a useful type. So, I mean, we haven't mentioned it yet, and I think it's nowhere mentioned in the slides, but nevertheless, it's a useful type. So why don't I use this now? That's called non-empty. Data list non-empty here. So that's in the base libraries, and it's a type for non-empty lists. And the constructor, so I mean, lists have two constructors, empty list and cons. And obviously then non-empty list only has one constructor. And it's an element and a list, a normal list. So this guarantees that it's always non-empty because there's always an element. So let me do this. So instead of lists, I say non-empty A. Right. Probably I have to import that at some point. So how do we do this? So we have this non-empty list. That's the constructor of non-empty lists. So how do I do that? Well, I pick a random index and then I use I return the element at that index, right? I mean, that's what one would do. So, right. So first I need, sorry, yeah. And I have this coin thing. And okay, sorry, I'm making that up while I'm in live. So just a second. I think it's useful to first have something like that gives me a random int in a range. So let's call it random int. So here the idea is random int n should give a random int in 0, 1, let's say n. Okay, so how would I do that? Well, I have my I could, never mind. I mean, it's possible to do this. I mean, the trick is, I mean, if you just have this coin, how do we do something like this? And one way is to do it recursively. Let's see. So random int. okay, first if it's 0, or let's say if n is less than or equal 0, then of course we have no choice. I mean, we must return 0. So it's just pure 0. Okay. So otherwise, okay. So now the idea is I basically flip my coin to decide whether I return 0 or not, and then I do it recursively. So with which probability should I pick 0? Well, there are n plus 1 elements. Maybe I should have done 1 to n. Is that better? I don't know. Doesn't matter. So in total, there are n plus 1 elements. So each should be drawn with the same probability. So probability 1 over n plus 1. So let me flip a coin with that bias. Coin 1 over n plus 1, but that wouldn't compile because I need to double and n is an int, so I have to do from integral. Okay. So if the coin gives true, then I pick the 0. If b, then pure 0. And else, so now I recursively call random int on n minus 1, but then I must add 1 to the result. So plus 1, recursively calling random int n minus 1. Okay, I hope this is clear so far. So I just, as a primitive operation for randomness, I can just flip a coin and I can give the probability that that coin returns true. So now using that, I want a function random int that gives me, given n, a uniformly distributed int from 0 to n. So if n is 0, the only choice I have is to return 0. But if n is not 0, my idea is, if, for example, there are 7 elements, then I flip a coin with a bias of 1 over 7. So if that coin returns true, I pick the first element, so 0. And if the coin returns false, I recursively pick a random number between 1 and 6, or 0 and 6, and then add 1 to it. Because, I mean, this was the 0 case, and so this is the non-zero case. Okay, and now that I have this helper function, now for the list stuff, I can just basically compute and use this random int to get an index. Random int, so between 0 and what? Well, that's the length of xs, right? So I mean, if, for example, xs has length 2, then the whole thing, the non-empty list, has length 3. So the possible indices are between 0 and 2, and this 2 is exactly the length of xs. So, and then pure, so if e equals 0, then x, the first element, and if not, then x as I minus 1. Okay, and now I get the error message that I must import data list non-empty with its constructor. Okay, and this is, okay, so far so good. So this is just to show, and I mean, right now it's all very abstract because we just have this class, but we don't have an example of a monad prop. So this is right. Okay, but this already shows, I mean, once you have such an interface and you just know it's a monad and it has a special operation, then you can do stuff with it. Now, of course, we would like to actually try this with some concrete example. And as a first example, I claim that IO is an instance. So we can make IO an instance of monad prop. Then of course I need function from double to IO bool. I need this extension again that we talked about before to give this type signature. Okay, and now maybe you saw already in the Cabal file, this irritating things in the way. I imported random. There were also exercises to that. Sorry. That you hopefully for the IO exercises have already done. But let me just check it out again. So we have this system random and there is this random IO. I mean, we used that for some example. We already used this. I forgot for which one, but last week we used it somewhere. So we have, for example, this random range IO thing.
And they also use it in the IO exercise.
Right. Okay. So I don't have to dwell on that too much. What was it called? Random.
RIO?
Yeah, that for example.
Yeah.
Right. So this is like that I can use. So I must just pick my range correctly. But I just one other thing. Sorry. I don't want to double here. I want a rational. Make it more precise. So the probabilities I want in rational, but I think that's everything should still compile. Right, doesn't matter. I want rationals, not doubles. So I don't have to worry about rounding errors and so on. Okay, so what do? I basically, so my P, I just, and unfortunately rational is not it's not an instance of random, so I have to convert that to a double. But there is this from rational function. And now I can just use random RIO. In principle, it's just 0, P. Why is complaining? Yeah, okay, fine. A P prime. Why is this
The
complaining?
type, I think it.
Right. This is a, sorry. This is of course a double. So this is some X. And of course, sorry. 0, 1. And now I just, the double is whether X is greater than, no, smaller than P. Pure X smaller P prime. Okay, so the idea is, how do I flip a coin with bias P? I draw uniformly randomly distributed double in the interval from 0 to 1. And then I return true if this random double is less than P prime and false otherwise. So if P is, yeah, and that's correct, I think. So, I mean, we can try that out, I hope. So I can say coin, for example, I don't know, 0.2 IO bool. Well, that's not very enlightening, but I can do replicate M20 coin. That's then 20 times flipping that coin. Right, and now if I did it correctly, it should roughly, I mean, like have 20% of this should be true and the rest should be false. Which, I mean, it looks
It's
sort of right.
actually exactly right.
Okay. So far, so good. Now we had these helper functions. Now I can try those. And actually, I can use another useful one, of course, is dice. So I can, for example, I have this random int, so I can have one die monad prop m int. So that's just random int 5, 0 to 5, and then adding 1. Doesn't matter, 1 plus would also be fine. Right? So now I can try that. So let's say replicate m 20 dice. So that's now IO int. And that also looks reasonable, right? So all numbers 100 dice. Okay. So this, yeah, just to show, but basically once I know how to do a random coin flip, I can do all other, other stuff. And this pick, we could also have implemented pick like so. So I could do pick from the list 1 to 6. I mean, that should basically, oh yeah, I need non-empty, sorry. So 1, 2 to 6. It also looks reasonable, I think. Okay. So far, so good. So I can, and maybe as a last example, I mean, of simple things I can do, I could do 2 dice. So throwing 2 dice and adding the results. I mean, in a lot of games you do that, right? So, I mean, one way to do it would be I throw my first die and I throw my second die and I give back the sum. But of course, we are all experienced applicative notation users now. So obviously we write it like so. Much nicer. And so I can try that out as well. We even have a 12, yes. So we have a 12 and we have a 2 and right. And the 7, I mean, as probably all of you know, I mean, if you throw 2 dice, then 7 should be the most common outcome. So far, so good. So, I mean, this is just to show, I mean, as in any other programming language, it makes sense to program against an abstract interface. So I just have a monad with coin, I mean, it's coin primitive, and then I can write my programs just using that interface without knowing what the concrete implementation will be. And then I can give an implementation in the form of, I mean, IO is an example where the implementation of coin just is that I use this system random module and basically use pseudo random numbers to flip the coin. And then these things work. But now the cool thing, of course, is that, I mean, I have this abstract interface, so nobody can stop me from writing other instances. And I mean, it is a bit annoying that, I mean, I try to test whether I did my implementations correctly, but it's hard to see, right? I mean, Robertino said it's exactly right here with the true false, but of course it would be nice if I could be sure. And I mean, for me, the coolest examples of a monad in Haskell is what I call probability monads. I don't know whether that's the official name. You can actually do this exactly. So we can define a monad that can do exact distribution calculations. So we don't need like sampling. I mean, this would be called sampling. So we draw random samples. I mean, from our coins, we basically make that experiment and then like do it 100 times. And then you could draw a histogram or something. We can just compute the precise distribution in one go. And as I said, I think that's super cool. So let's define a new type for that because we want to give it like monad instance and so on. And I mentioned that before briefly, I think when somebody asked, so let's call it, I don't know what to call it, R list or no, let's call it distribution, distribution A. And it's distribution get, let's call it dist. Otherwise, I type too much. Get dist. And it's simply a list of A's paired with rationals. And the invariant, all rationals are in 0, 1 and add up to 1. So this is something I can't express in the type system. So I must basically make sure that that's always true. So I don't allow any odd list here, only those where all the rationals are between 0 and 1, and the sum of all the rationals in the list is 1. And I can even give a show instance for this. Okay, now I claim I can make that an instance of monad. So sorry, functor I need. Applicative on monad. And of course, the idea is that this represents a distribution. So for a given A, it tells me the probability that I will get that A. So that's the idea what this type represents. Okay, so now following the recipe for monads, so we implement pure from applicative. So it's of type A to dist A. And pure, as I've like said dozens of times by now, the idea is always it doesn't have the potential side effect. It doesn't make use of the side effect. So in the case of probability, the side effect, of course, is randomness. So pure means there is no randomness. It's like a certainty. So that is represented by the distribution that has only one possible outcome, namely A, the given A, with probability 1. And I must just use my new type constructor. So that's pure. And now I need bind. I mean, that's always the most interesting one. Almost always. So given a probability distribution of A's and the function from A to distribution of B's, I need a distribution of B's. So if I have dist, maybe I don't even need this get this stuff. So let's keep it simple. So I have a distribution of A's and some sort of continuation. So let me first find make the rest the errors go away. So my whatever it's called, I define as app, and for that I need to import it from control monad and functor fmap as always we define as lift m. Okay, so that's all the boilerplate. Can give the signatures as well if I want. Right, so all that's missing is the bind. Okay, so, and this is just like high school probability. What did I do now? God only knows. Oh, I don't know what I did. I don't know.
I think it's the gist at the end, line 56, isn't it?
Yes, yes. This XS. I don't know why I deleted everything. That was some quirk of my editor again. Whatever. Okay, so now I'm where I was before. Right. So how do we do this? I think this is a nice example for, I mean, what happens? So we have a distribution. So we have pairs, I mean, a list of pairs of A's and their probabilities. And we now will, depending on, so, yeah, okay, fine. Maybe do notation is good. So first this is now in the list monad. So maybe I should make that explicit in the list monad. So we grab one of those pairs, so x comma p. So this is one possible outcome of the first distribution. So it's an A, maybe I should call it A. So it's an A and a probability that that A happens. So now if that in a world where this A happened, so now we have our continuation K, so we can apply it. So let's do this. So dist wise K applied to A. Okay, but this is now not the right. And what is now the probability? So we have these YSs, but the probabilities of those outcomes are only under this. I mean, if first we drew the A with probability P, so we must scale all the probabilities in here by P. So we have pure dist. Okay, so if I have a B and a Q from this Ys, then I want B P times Q. Now I get millions of errors. Why? Second. Some silly mistake somewhere.
Oh, I think you might be wrapping it twice at the end, or
Right. Yes. Exactly. No.
and at the top.
Yeah, like this. Right. Yes, that was what I was doing. Okay. So I mean, the idea is just, I mean, I have like a distribution. So A's with probability P. Now I do this K thing, which gives me a distribution of B's, but each of those has to be, so BQs, but each of these Qs has to be multiplied by P because the A only happened with probability P. So, I mean, that's one way to write this. And okay, so that's a monad, but of course, we want it to be a monad prop. And I hope this becomes then also clearer. Monad prop dist where? So we need this coin. Rational to dist bool. And this is now very simple. And this is the whole point of this exercise. So it's, well, with probability P, we get true. And with probability 1 minus P, we get false. And there must the dist constructor. And there's maybe one last thing. I mean, I just want to be sure that my invariant holds. So if the P is in the wrong range, so I can do, I always have to concentrate, min 1P max 0. I just, if it's not in 0, 1, then I just squash it into 0, 1. So just so that it's guaranteed that my invariant here holds, that the probabilities are always in 0, 1. Okay. And now we can try everything we did in IO, because now we have a second instance, we can try it with that. So what all did I try? So let's see. So first, for example, I did 20 coin flips. So instead of doing it in IO bool, I can now do it in this, but this will be right. This is very bad. So let's first do something else. I mean, let's only do 3. Right. And now we see this. So for example, I get true, true, true with probability 1 over 125 and true, true, false, blah, blah, blah. But now one annoying thing is that there will be duplicates in this list, I think, or maybe not in this one. Oh, no, they are not. In this one, they are not. So that's all good. Right. I mean, everything should be right. So, and I think it's also correct. I hope. I mean, it was I did coin 20% probability for true. So to get 3 trues would be 20% times 20 times 20. So it's 1/5 cubed. So that's one. Yeah, that's correct. Okay, that's good. But now let's try these 2 die. It's just not replicate one. Just, I mean, we don't need the replicate was only because if we are sampling, we need to do it a lot of times to see a pattern. Now we actually don't need this anymore. So we can just do one, like I did 2 die, 2 dice. So that's a dist int. Well, let's first do 1 die. Okay. And we see, okay, we get 1 with probability 1 over 6, 2 with probability 1 over 6, 3, 4, 5, 6. So that's good. So now let's do this 2 dice thing. Okay, and now we see that, for example, the 7, I mean, everything here is with probability 1 over 36, but we just see that we have duplicates. So we have like the 7 several times. So this is correct, but it's a bit annoying. I mean, we would like it to be like only one entry per thing. And so actually, instead of what we actually want, instead of a list of pairs, we would like, I mean, what we would like here is actually a map from A to rational. So that we can basically, if the same A appears several times, we can sum up the probabilities. But the problem is that, as I explained earlier in this lecture today, that for map we have this constraint, the odd constraint. So that would only work for odd A's. But I mean, monad and functor and applicative don't allow a constraint on the A. So we can't do that. So that's a bit annoying with this approach. And there are several ways around, but I think the easiest is to just write a summarized function that, given a dist A, just converts it into a, and if I have an odd constraint on A, just gives me a map from A to rational. So now I have to import again, like I explained earlier, data.map map or qualify data.map as map. Okay. So this is now standard exercise in fold left. So dist xs. So also annoying that one always has to import that, even though it's so common. And data.list. Okay. Yeah, yeah. Okay. So it's a fold left prime. Let's call it F. We start with the empty map XS, where, so XS. So the accumulator is now of this map type. So we have a map A rational. We get a new entry from the list. So we get a pair of an A and an rational. And we must update the map. Okay, and there's a, I mean, the point is now there are basically 2 cases. If the A is already in the map, we want to add the P to the value that's already in there. If A is not yet in the map, we want to insert it. So we could do that explicitly, but we don't have to, because there is a nice, let me just write undefined here so that not everything is horrible, and that's of course not XS, that's F. There is map insert with that takes a function from A to A to A, and the key and the value and the map, and updates the map. And what it does is exactly what I said, basically. So if the key is not yet in the map, it just inserts it. But if it's in the map already, it uses this function to combine the value that's already in there with the new value to a final value. And we want plus. So we can just use map insert with plus a p m. While complaining. Okay, this is again this for all 8 thing, the scope type variables. Same problem, same solution. Okay, and now we can get that nicer. So if we reload, so earlier we had this 2 dice, and now we can summarize 2 dice and get a map from into rational. So now everything should be nicely summed up. And now we get what, I mean, what everybody knows, that if you roll 2 dice, then 2 and 12 are most unlikely, only probability 1/36, and 7 is the most likely and has probability 1/6. Now we can also check whether our, for example, our pick is correct. So let's say summarize pick, let's say A, B, C. So a 3-element list. What now? Oh yeah. Yes, and that looks good. So we see that with my implementation of pick, we get A, B, and C with equal probability of 1/3. And we can do it with longer list as well, and we get it with equal probability. Right, so now we have this abstraction monad prop. So we have seen that you can like do simple probability. I mean, using this coin primitive, you can do stuff like an arbitrary integer between 0 and n, throw a die, pick a random element in a list, throw 2 dice, and we have 2 implementations for this monad prop IO, where we sample randomly or pseudo randomly. And what I still find very cool, even 20 years or so after I first learned about that, that you can basically get exact probability distributions. And I think now we should have another short break, and then I want to apply that to the famous Monty Hall problem that has baffled even Nobel Prize winners and famous mathematicians. So maybe we have another short break, 10 minutes, and then I do that.
Okay, so quarter past?
Yes, let's say quarter past.
Yes.
Okay, talk to you then.
See you then.
Okay, can we continue?
Yeah, sure.
Great. So Monty Hall. There's a nice Wikipedia page for that. So it's as it says here, it's like a brain teaser or probability puzzle. And so the idea is there's some sort of game show where in the end, I mean, one candidate wins and then the candidate has the chance to win a car. But he has to basically gamble for that car. And there are three doors hidden, I mean, closed doors. And behind one of the doors is a car, and behind the other two doors is a goat. I mean, maybe, I mean, in Kenya, I mean, you love eating goats, so that's maybe bad, but I mean, it's supposed to not be great to get a goat. So people prefer the car. And right. So the idea is the candidate picks picks one of the three doors, and then the host of the game show opens one of the other two doors that the candidate has not picked, but one behind which is a goat. So for example, the candidate picks door one and then the host opens door three and there's a goat. And now the twist is that the candidate now has a choice. He can stick with the door he originally chose, or he can change his mind and pick the other one. I mean, one he chose originally, one the host opens with the goat behind, and he has the chance to switch to the other closed door. And the question is, what should he do? I mean, there's no guaranteed way to win the car, but the question is, can he increase his chances by switching the doors, or should he just stick with his original choice, or doesn't it matter? And I mean, in principle, that's like a simple problem if you think about it and if you know something about probabilities. But the interesting thing is, if you can read up, if you're interested in this article here, that it seems to be deeply wired into our brain that we get that wrong. And there were like famous mathematicians and Nobel Prize winners that not only get it wrong, they even insist that they are right and are very hard to convince that they are wrong. So yeah, and now using the machinery we built before the break, we can easily settle that once and for all in Haskell and get the actual probability for the strategies. So let's see how we can do this. So maybe like always in Haskell, start with the types. So for example, we have price, can be a car or goat, let's say. I don't know what we need, but can do show, read, ecort, definitely. Could also have bounded and enum. I mean, we don't need this, I think, but whatever. Okay. And maybe a strategy, which can be either stay or change. And then now let's model the Monty Hall, the whole thing. So given a strategy, if we have a probability monad, the probability that the candidate gets his car. Okay, so one step at a time. I mean, first we have to figure out where the car is and where the goats are. So there are three doors. Can simply model that as a list with three elements. I mean, to keep it simple. So let's first randomly use our random int. So let's call it car index. So we use this random int we defined with 2. So 0, 1, or 2. So let's call, I mean, we have a list with three elements, so the indices are 0, 1, 2. So car index is now the index where the car is. So 0, 1, or 2. Okay, and now let's say the candidate picks picks his original, it doesn't matter. I mean, we could also hard code it, but let's say first choice of the candidate is also, randomly one of the three doors. I'm not sure whether I even need this price type. Probably not if I do it like this, but let's see. We can delete it again. Right, so that's that. So now the host opens one of the other doors, but one that contains a goat. So let's see. A priori, so he picks from a list of indices. And what is this list? So let's call it host opens. So he picks from a list. Let's think about this list. So originally, there are these three doors, but the host cannot pick the one that the candidate chose. So he must open one of the other. And he can't pick the one containing the car. Sorry, car index. Let me just put an undefined there so that, what's this now? I need this non-empty. That's a bit, yeah. We know it's non-empty, right? There are three doors, and if these two are different, then there's still one door left. So at least one door is left, or two that the host can open. We know that, but it's difficult to convince Haskell of that. So there's a function in non-empty, which is called from list, I think. So it converts a list to a non-empty list, and that is of course a partial function. So if I apply that, sorry, qualified, no, sorry, as non-empty, then it crashes. So just give him a second. So let me apply that here, non-empty from list. Just to demonstrate, so non-empty from list, whatever, ABC is this. But if I apply it to an empty list, it crashes at runtime. But we know it's not empty, right? There are three possible doors, and at most two of those the host can't pick. So at least one is still possible to pick. So it can be one or two. And we pick, so the host randomly opens one of the two containing a goat. Okay, and now the final choice now depends on the strategy. So if the strategy is stay, then he doesn't, then it's the first choice. The candidate doesn't change his mind. And if it's change, well, then it's the remaining door. So what's that? Let me do this again. So we have our three doors, one index. So he wants to change. So he doesn't want his first choice. And of course, he won't pick the one that the host, or he can't pick the one that the host just opens. And we know that only one, so this list here will have exactly one element. So I can take the head of that. Okay, so that still compiles. So I hope this is clear. So if he wants to change, so he picks another door, not the one he first chose and not the one the host opened. So the third one, the remaining closed one. Okay, and now did he win? Well, he won if his final choice is the car index. So pure final choice equals car index. And that means we indeed don't need this nice type, pity. There are ways to do it with goats and cars, but Okay, so that's it. And now we can just calculate it. So I mean, if to make it more to make it more suspenseful, let's first try it in IO. So if we do replicate M10 Monty Hall stay, IO list of booleans, whatever I did there. Let me just get, yeah, okay. Or maybe let's let him play 50 times or 100 times. So, I mean, it's hard to see, right? But there seem to be more falses than trues. So it's not very good, it seems. Let's see if we sample with strategy change. I mean, on first glance, that looks much better. But I mean, that wouldn't convince the skeptics. But now we have our cool exact distribution monad. So we don't need to do it 100 times. We just calculate the probability directly. Stay. Now dist pool. Okay, and sorry. I want to summarize so that I get a nice map. Okay, and this is, I mean, as expected, if he just keeps with his original door, then, I mean, he has a 1 in 3 chance to have picked the car. So that sounds right. And now, of course, the crucial thing is what happens if he changes? And tada, he can double his chances. So he should change. But as I said, even Nobel Prize winners don't believe this, even though it has been proven over and over again. And there are simulations. And I mean, I once convinced somebody by just doing it with dice and just playing that thing 50 times or so. But yeah, so I think that's really cool that you can do things like that. And it's right. So it's an example, another example for monad. So we have this dist thing that's a monad. I mean, I didn't prove the monad laws, of course, but they more or less follow from the monad laws for list, plus the rules of probability. And I think it's a very nice example. So I mean, it's an example for like programming against an abstract interface. It's an example of monads. It's an example with the summarize of what we talked about in today's lecture, this map type. And yeah, it's an example that, I mean, what things you can do in Haskell. So you just have this probability experiment, like this game show thing, and then you model it in a suitable monad relatively naturally, as I did here. And then you have your distribution. So are there any questions to that?
Not so far. Maybe I'll give it 30 seconds.
Mm-hmm. Sure.
No questions. It seemed convincing.
Good. I'm glad. It's really funny. I mean, I read this Wikipedia parts of the Wikipedia article today during lunch, and even Paul Erdős, one of the most famous mathematicians of all times, he remained unconvinced until somebody showed him a computer simulation of this game that finally convinced him. So I don't know. And I also read in this article that seems the human brain somehow is wired that all unknowns have equal probability, even if they don't have. So it seems to be something rooted deeply in our psyche that we get this wrong intuitively. People just can't believe that it can make a difference to change. but it does. You can double your chances on the car by switching your choice.
And Samson says, very convincing. Why did we drop our fancy type of price?
Oh yeah, originally, I mean, you have different choices how to model this. I mean, I now just work with indices. I think when I did it in the Mongolia class, I actually had a list representing the door. So it was like goat, goat, car, or car, goat, goat. Then I needed this. But I mean, in this way, I don't even need that. I mean, there's not just one way to model this thing. So yeah, I mean, here I don't need that anywhere because I'm just working with the indices directly, the list indices. Are there any other questions?
Nope.
Okay, so now what do we do? We have half an hour, I think.
I don't know. Maybe we could. There was some questions about tail recursion. Not sure if we don't want to spoil the
Right.
answer, but maybe we could talk about maybe transforming some simple data type from like some simple processing function from recursive to tail recursive, or just starting with the next lecture.
Yes. Do you have an idea for a simple example of tail recursion? I mean, the one in the assignment is with trees, right? And that's relatively complicated.
Yes. Yes, it's a tree without value at the node, just leaves. It's a simple tree. It's a binary tree without value at the nodes. So
Yes.
maybe we could redefine fold air, fold R. That will be a bit too repetitive though.
Right. I mean, with lists, is it?
We can do it with lists.
Right. Yes. With lists, it's easier, but yeah. I mean, I'm not sure whether that's efficient or anything, but yeah, we can do this. I mean, for example, I mean, just as a general idea how it works. So if I go back to this,
maybe we can process it in like with a specialized function, like sum or something like that.
yeah, exactly. I think I have an idea. Let's see. I mean, my sum I have stuff into int. And this, for example, that's not tail recursive, right? I mean, maybe that's too simple, but the point is it's not tail recursive because after you return from the recursive call, you still have to do something. You still have to add X to it. I mean, tail recursive means that the recursive call is the last thing you do. So this is not tail recursive. And the idea of making something tail recursive is basically always giving it this continuation, what to do with the result once you are done. So the idea is my tail sum prime. It gets a continuation. In this case, from int to int, what to do with the result afterwards. So continuation, and for the empty list, it just applies the continuation to 0. And if it's non-empty list, then it tail recursively calls it on XS. And then what must it do with the result? It must apply the continuation to X plus the result. And this is now tail recursive. The last thing we do is the recursive call. And now one can like turn that into what we actually want. By using it as the continuation. I mean, that's an example. And of course, basically what we do with accumulator is more or less the same thing. It's just, what's that called? Defunctorialization of this continuation by explicitly having this accumulator around. But this is the general idea. And I mean, it works the same for binary trees in principle. That's always the idea. So you add this continuation, and somehow the continuation encapsulates how you get from your recursive call to the final result. And I mean, that's like the general recipe to make something tail recursive.
And yeah, and if it's more complicated than that, you can use like helper functions, like a Go, like Lars
Yes.
always. Oh, yeah.
Right.
I think more hints than that will be too much.
Yes. I mean, this is, yeah. Right. Are there other questions or other stuff I can do for?
That was the only question about the homework. Just a reminder, we have 4 more days to complete the homework. Make sure to push the changes even if it's not finished. And as far as I know, that's it. Maybe, do you think we should start? We have 20 minutes. Should we start next lecture or?
Let me just check what that.
We can do that next week.
Let me just see whether there's a like something that would make sense. I mean, to do. I mean, maybe actually.
Maybe other string types. That's not terribly complicated.
Right. Okay. Let me just see how many pages that are. Yeah, that's fine, I think. Yeah. Right. Yeah, we can do that. I mean, we have mentioned that before. So strings. I mean, as we know, I mean, we learned that right in the beginning that in Haskell, string is just a list of characters. And it's very nice to work with that, because then automatically you have all the, I mean, as we said before, I mean, like lists are the working horse of functional programs. I mean, lists are everywhere and are used all over the place. And because you can work very nicely with them in a functional setting. So by making string just a list of characters, I mean, it's conceptually very pleasing and simple. And all the functions you have for lists automatically then also work for strings. So, I mean, you don't need any special function to concatenate strings, for example, because, I mean, we can concatenate lists and then that automatically works. Or, I mean, the standard example that I always use is to upper. I mean, we have map for lists or fmap. So we automatically know how to do something to every character in a string, like shout. I mean, by just mapping to upper over the string. So that's nice. But actually, I mean, if you want to do serious text processing with larger text, it's horribly inefficient. Here's this question: how much memory is needed to store a string that's 3 characters long? And yeah, I mean, the details are not important, but we saw this diagram earlier of lists with these const cells. So each const cell is 3 words, info table, and 2, yeah, I mean, basically the tag that it's a const, and then 2 pointers, one to the head and one to the tail. And the characters are boxed, so they could be thunks because of the laziness. And so the box itself is again 3 words long. Info table, 2 words for the character, 2 words because it's Unicode, so it can be, I mean, 1 word would not be enough, I think. And the empty list is 1 word, right? And if you add all that up, then you get 128 bytes on a 64-bit machine, which is sort of horrible because, I mean, it should be like only a handful of bytes for 3 characters, like 6 or so. So it's very memory inefficient to use strings. I mean, especially for large texts. And yeah, okay, fine. So the empty list is shared. Some frequently used characters may be shared as well, but still. And so there are various alternatives depending on what you want to do. But if you really want to do text processing, like human readable text or programs or what, I mean, something like that, I mean, really Unicode processing, then text is probably your best choice. And that's like an abstract type, so it's not something concrete like list of characters. And it's a packed representation of Unicode text. And it uses much less memory than string, and something like 2 bytes per character. And the performance is also much better than for lists. So we saw earlier that lists are only like efficient if you operate in a stack-based manner, basically only manipulate the head of the list, but they are more like sequences or something. I don't actually know how they're internally implemented, but I assume it's more like these sequences. And to go back and forth between string and text, there's pack and unpack. So that's like inefficient or takes long, so one shouldn't do that too often if you can avoid it. But it's possible to go back and forth. And then there are, I mean, here these operations. So you can basically, you have the same things you can do for strings. You can also do for text. So you can append a character to a text. You can concatenate to a text. You can get the length of a text. You can map a text, but this is now specialized. I mean, the result type must also be characters. So this to upper, for example, would still work. I could use this. Can filter text, fold text. Okay, to upper seems it's built in more or less. Strip removes white space from the ends, convert it into a list of text line, so it splits it at new lines. Get the head of a text, last character of a text, and you can also index. And this is, well, I mean, not as so what I said earlier about sequences, I take that back. So it's obviously not sequences, because then this would be logarithmic. So it's not as good as sequences. But the point of text is basically that you have like this compact memory implementation. And there are also, I'm not sure whether it's mentioned in the slides, but there's also something called text builder, which makes it efficient to concatenate text or several texts to concatenate them together. So yeah, so whenever, I mean, especially in modern libraries, if there's any interaction like with text coming from the user or from a file or so, they normally always use text and not string for that. So the rule is basically the same as for lists, what we said earlier. I mean, if basically you are only dealing with strings of a fixed length, you know everything is shorter than whatever 100 characters or 1,000 characters, then it's fine to use string if it's simpler. But if you don't know if it's unbounded because maybe you are reading a text file from hard drive or getting a web page over the network, then where you don't know how long it is, and it can be basically be arbitrarily big, then one should always reach for text. I mean, if it is text, if it's like Unicode. Okay, so there's that. And there are also lots of, I mean, we can look at it in package. So text package.
The first day, Lars said that there are more than the standard prelude. There are like alternative preludes from other people, and plenty of other preludes use text directly instead of the list of strings, of list of cards.
Right, yes. And in particular, there's also something here, data text IO. So a lot of these IO functions we used as examples, like read file, write file, and get line and put string line. Here there are variants with text. So you can like read the file context of a text file with read file, and you immediately get text and not string. Or you can this get line, put string line, and so on. So there are basically all these things are with a text version instead of string. And another good one or important one is this data text encoding. Okay, but we come to that in a second. Right, so that's text. So whenever you deal with like larger bodies of Unicode text, you should reach for that. And there's also something like, I mean, I think there's an exercise to that, so we shouldn't dwell on that. Something called stream fusion. So there are very cool optimization techniques that one can use when one does functional programming that the compiler can use. So sometimes like two maps or map and a fold can somehow be where you normally think you would need to traverse the whole thing twice or several times. That can be done in one traversal. And there are all sorts of optimizations built into this text package that try to do these things automatically. So it's very performant and fast. And there's extension. I mean, that's also interesting and useful to know. So if I mean, if I ask for the type of the character, or this, sorry, not the character, the string X, it is string. Whereas if you recall, if I ask for the type of 42, then it's not int or double or whatever, it's basically polymorphic. Any numeric type, this 42 can be of any numeric type. Whereas string is just string. But there is an extension. It's called overloaded string. I can also do that in the GHCI directly. So that's the same as if I would say language overloaded strings in my module. And if I do that and ask for the type of X, it's no longer a string. It's basically similar now to num_a. And so we can ask, what is this is string type? The class, I mean, sorry. And that just has one method, from string. So it can convert a string to a. And there are, I mean, here now we don't see any instances, but that is because I haven't imported any other modules. But if I, for example, do text, add that to my dependencies and byte string, we will come to byte string in a second. Let's reload. Okay, and go back into the REPL. So now if I import data.text text, and now if I ask again for information on, sorry, if I import data.string, ask for information about isString. Now I see that text is also an instance. So that means now I can also use a string literal like Haskell and say that's of type text. Okay, I must X overloaded strings again. Right. So with this, I mean, if you work with these other string types like text, then it's often a good idea to activate this extension overloaded strings, because then literals, string literals that in standard Haskell only, I mean, they are not polymorphic, they are always of type string, then suddenly they are polymorphic and can also, for example, be of type text. But of course, then you have the same problems as with numeric literals, that sometimes the compiler doesn't know which type you mean, and then you have to give type on annotations. So yeah, it's a double-edged sword. But nevertheless, you can do that. So that's text. And right. There's also something called data text lazy. Yeah, so it's a variant. It basically has the same API as text, but it means you don't have, if it's long text, they are then split in chunks, and the chunks basically are only loaded on demand if you need them. So it can be more efficient for like big texts where you don't need all of that in memory at the same time. And there are also conversions, so to strict and from strict, to get from a lazy text to a strict text and the other way around. And the lazy text is also an instance of isString, so you can also use that with string literals. Right, and as we saw, appending of text is not very efficient. That was O of n. So for that, there's so-called builder. And that's, for example, in data, or that is in data.text.lazy.builder. And you can convert to and from builder and lazy text. And I mean, builder to lazy text, strict text to builder, lazy text to builder. And then the clue, I mean, the why you would bother with this builder is that then concatenation is constant time. So if you have some task where you assemble like a big text from smaller pieces, so you do like lots of concatenations, then it's a good idea to use this builder, because that's much more efficient than doing it with text directly. So you would use the builder to assemble your pieces, and then when you are done, call this to lazy text or to text. I think there's also a to text. And so then you only have to like pay this cost of O of n runtime once in the end. Right, so that's text. And then I also mentioned that at some point, I think, another textual type is like binary data. And for that, we have the byte string package in Haskell. So that's bytes. So it's basically, I mean, you can sort of think of it like a list of bytes, but again, it's much more efficient. So it's just bytes. And again, much less overhead than string, even less overhead than text. But the characters, the bytes, a priori have no interpretation. So it could be Unicode, it could be ASCII, it could be whatever encoding. It doesn't even have to, can just be really binary data, like a movie or a picture. So it doesn't necessarily have to be text. And yes, so for example, good for real binary data, or if you have like something in ASCII format. And again, they are like strict and lazy variants. And again, both are instances of isString. So I can also have, if I import data.bytestring. So now my Haskell, I can also make it of type bytestring, for example. And it looks like this. I mean, again, looks like that, because Haskell is ASCII. It would look weirder if I use like non-ASCII characters. I am not sure what happens if I use my name, for example. Not sure what it does then. I can't in the console. Not sure. Yeah. Okay, so that's bytestring. And then there are also ways, that's what I want to show you earlier. There's this data text encoding, where there are functions to get between byte string and text with different encodings. So there's Latin 1, ASCII, UTF-8, and then there are versions. Lenient means if it finds something that's not a valid Unicode character, it just replaces it with this thing, whatever that is, like a box or something. And then there's a strict variant where if it encounters an error, if there is an invalid, that's something that's not Unicode, then it gives you a left error. And if all goes well, right text. And similar for ASCII and then I mean, these are all the decode functions, and I'm sure there are also encode functions somewhere further down the line. So yeah, here. So you also get all sorts of encodings, whatever, Unicode and ASCII and so on. So this is sometimes, I mean, I think we also have exercises for that, especially when you deal with blockchain or stuff or network protocols. I mean, this is always a headache I mean, because there are so many different encodings. I mean, you get hexadecimal and base 64 and base, I don't know what all, base 16, base 64. And then, I mean, Unicode, ASCII, all these things. But basically, for everything you can think of, there is something on Hackage. So so it's all, but I mean, often it's quite. I mean, you have to do a lot of conversions to get the encoding right and convert it, and then strict and lazy. And some libraries use strict byte strings, some use lazy byte strings, and some use base 64 encoding, and so on. But there's always a library for that. I mean, for example, if you want like base 16 package, there's data byte string base 16, and that's encode something as hexadecimals. So here's an example. So it would encode the byte string foo as these three, what's it called? Whatever it's called. This,
Decimals? Or...
yeah, I think, yeah, whatever. Or there is, if you Google base 64 package, then there's base 64 byte string, and then you can encode to base 64 and decode. So yeah, it's always looks more or less the same. And here you see they also have this lenient and the strict variant. So where if something is not valid base 64, you get an error. And otherwise it replaces it with something. Yeah, and often as I said, I mean, that's like if you do practical Haskell for real world problems, often you have to deal with these things that you need some special encoding or decoding and so on. But that's all available on Hackage. Right, I showed you the encoding, the decoding. Here it still says on the slide it can fail, but as I said, there is this lenient version. And now I think that's in relative modern versions of byte of text. Earlier, they only had this strict one where you then get an error. Right. And you can also, I mean, we now know you can convert between string and text with pack and unpack, and between text and byte string with all these encode decode things. You can also directly convert between string and byte string if you know it's as ASCII, and that is defined in data text char 8, character 8, or whatever, char 8. And that can both go wrong. So if your string contains characters that are not ASCII, then that will fail. And other way around as well. So that's also possible. And as I already showed you, yeah, I mean, there are all these conversion libraries. And of course, on Hackage, there are also not just the containers and these text packages, but also everything you can think of I mean, there are also hash maps. I mean, the maps I showed you and that we normally use are, as I said, based on balanced trees. But I mean, in other languages like Python or Java or whatever, it's I mean, the most common data structure for these dictionary types is like hash maps, and there are also hash maps available on Haskell. I personally never use them, but I think actually in the Node we do use them. So I mean, some people use them a lot. And so yeah, everything you can think of, I mean, it's somewhere on Hackage. Right. So yes, I think we should stop here, and then we have already done one chapter of the next lecture on Monday. So we have more time for other things. So we're almost, yeah, we are done actually with the time, but are there any questions?
Not yet, but waiting. Seems like there's no. Oh wait, you said builder had a compile time of question. And builder had a compile time of.
I mean, I didn't say anything about compile times.
I think maybe he means
Runtime.
runtime.
I mean, the point is, if we look at text, concatenation of text is O of n. So it's linear in the length of the text. I'm not sure whether it's the length, probably the length of the first text. And that's similar to the like asymptotic runtime of lists. I mean, concatenating lists. That's like
Yeah, I think it's a
proportional to the.
synonym actually for the string.
Yes, yes. Anyway, so it's like if you concatenate long text, then that takes a long time. And the point of builder, I mean, the cool thing about builder is this line here, that concatenation is constant time. So if you want to, as I said, if you need to do a lot of concatenations, so if you have to, I mean, assemble something like a web page or whatever, or a book from chapters or something like that.
Process text for an AI.
Exactly. If you build a prompt for an AI and have lots of concatenations, then it's more efficient instead of concatenating the text directly to use the builder. And then when you are done assembling your text, use this to lazy text, or I think there's also to text to get to text. So that's more efficient. So there's an efficient way of concatenating text by using this builder type. So,
Okay. Says thank you.
okay. Anything else?
Not so far.
Okay.
We're on time as well.
Yeah. So then the plan is to do the next lecture on Monday, right? Same time.
Same time. Yeah.
So from now on, like by default, every Monday and Thursday. And if something changes for whatever reason, we'll let you know in advance, of course.
Yes.
Okay. Then thank you very much.
Thank you, everyone.
And talk to you on Monday. Have a nice weekend, everyone.
Bye.
Thank you. Bye.